On our first exam question, we are going to look at this one. This is question 2 from Spring 2015 question paper 43. And the question says this. Particles A and B of masses 0.35 kilograms and 0.15 kilograms, respectively, are attached to the ends of a light inextensible string. A is held at rest on a smooth horizontal surface with the string passing over a small smooth pulley fixed at the edge of the surface. B hangs vertically below the pulley at a distance h meters above the floor, and then A is released and the particles move. B reaches the floor and A subsequently reaches the pulley with a speed of 3 meters per second. First question is, explain briefly why the speed with which B reaches the floor is 3 meters per second. So again, what's going on over here? I made a diagram. Also, that's basically this. And what is going on over here? This is a frictionless surface. So every time you read this word, what does this mean? This means that you don't have to worry about any forces countering the motion, right? The only force that matters to the motion of this ball is this tension over here. Where does this tension come from? It comes from the fact that this ball over here is hanging, all right, and is making this string taut. So what is going on? Let's focus first here on B, because B is the ball that is causing the whole motion, right? So when this is released, what are the forces that are at play in this situation? You have the weight of B down, you have a tension up, and you have a tension over here. And in the perspective of A, never mind the weight of A in the normal contact force, because they are vertical. They don't contribute at all to whatever is going on the horizontal axis, on the axis of motion. This is the only force that A is submitted to, if you exclude those two. So this means that A is going to move no matter how heavy or light this is. All right. The only thing that the weight of B is going to affect is the acceleration with which A is going to move, but not the fact of whether A is moving or not. All right, because you don't have any force countering, no matter how little this tension might be, or may be. All right, so what is going on then? You have B with a weight down, you have a tension up, B is going to move, so this means it's going to accelerate downwards, so this means that the weight needs to be bigger than the tension. And since you have a single string passing over a smooth pulley, this means that this tension needs to be the same as that one as well. So these two tensions are the same. This weight is bigger than the tension. And these are the forces that are at play over here. So you let this go, this one goes down, this one goes that way. And every time you have a situation like this, the acceleration of the system is the same, meaning that the magnitude of the acceleration of B is the same as the magnitude of the acceleration of A. This means what also? This means that when B hits the ground and stays there, you will no longer have a tension over here, because due to inertia, this ball is going to continue moving, right? But since you don't have this tension anymore, the string gets slack, right? Since you don't have this tension anymore, now, horizontally speaking, you have no other force acting on A, right? So whatever the speed A had the moment B hit the ground, don't forget that the speeds of A and B at any single moment, as long as the string is taut, they are the same. The speed with which B hit the ground is the same as the speed that A is going to continue having until something interferes with the motion, which is going to be the pulley, right? So the answer for 1 is, while A and B are moving, before B hit the ground, they both have the same speed. The moment hits the ground, there will be no more tension, and since there is no friction in A, then it will continue moving with constant speed, and a constant speed is 3 meters per second. So this V of A is going to be the V of B the moment B hits the ground. Okay? Then the second question was, find the value of H, the height of this. The best approach to answer this question is to look at this as a single object. What do I mean with being a single object? If you consider this as a single object, all internal forces are taken out of the way. And what are the internal forces in these cases of pulleys? Is it the tensions are the internal forces, right? Don't forget that now, when you have pulleys, I will consider one direction, the direction of motion, instead the horizontal or the vertical, right? So this system is going like this. So this motion is going to be, for example, positive, and any attempt to counter the motion is going to be considered negative. So this tension, for example, is positive, this tension is negative. And if you consider this as a single object, you have two forces of equal magnitude and pointing in opposite directions, so they cancel each other out, right? This means what? This means that for this system, considered as a single object, the only resultant force is going to be this weight over here, all right? Anyway, I just wrote over here the equations that you will have for A and B. So in relation to A, you just have the tension equals the mass times the acceleration, the mass of A times the acceleration. For B, you have two forces. So the weight of B minus the tension equals the mass of B times the acceleration. But for the system as a whole, then you may consider the single resultant force, which is the FB, the Fg of B, the weight of B, equals the total mass of the system, which is ma plus mb, times the acceleration. Don't forget again that the acceleration of the system, as long as the string is taut, is going to be the same. So all of these are the same. So which one you pick? This one is a simpler one, right? What is the weight of B? Is m of bg equals m of a plus m of ba, right? And then it's just a matter of substituting. A is going to be 0.15 times 10, so 1.5, divided by 0.35 plus 0.15, and this gives a value of 30 meters per second square. Now that you know the acceleration, you have everything you need to get the height, all right? Because the initial speed over here is 0. The speed with which it hits the ground, the question said, and you answer in 1, is 3 meters per second. You know the acceleration, so you can use this formula, v squared equals u squared plus 2ah, now adapted to the situation. And h equals v squared minus u squared over 2a. Just substitute, and you'll get the height of 1.5 meters. Okay? So again, a total of 5 points for this question. Don't forget, pulleys, the key elements to retain is tension in a single string is the same, the magnitude is the same, and the acceleration of all the both objects connected to the same string is the same as long as the string is taut. If you have these two things in mind, then it's just a matter of putting them in the corresponding formulas for every single object and for the system as a whole. And then which one you use depends on the situation that you are being asked, and you have to by a force of experience to know which one to use. Let's look at one a little bit more complex. This one is from winter 2013. It's question paper 43, and we're looking at question 2. Let me put this bigger. And it says, particle A, this one, of mass 0.2 kilograms and particle B of mass 0.6 kilograms are attached to the ends of a light inextensible string. What does this mean again? Light inextensible string means that you don't have to worry about the properties of the string. It's something that is there. The mass doesn't matter. That's why it says it's light. Inextensible means that it cannot be extended. So you don't have to worry about the fact that the weights may extend the length of the string. All right. Basically, you don't have to worry about the properties of the string. The string passes over a fixed smooth pulley. Smooth pulley means what? Means again that you don't have to worry about any friction in a pulley. So the only thing that you have to worry about is A and B, and this is going to be the situation in every single exam question regarding pulley. The strings are always light and inextensible, and the pulleys are always smooth. Then B is held at rest at a height of 1.5 meters above the floor. A hangs freely at a height of h meters above the floor. Both straight parts of the string are vertical, okay? And then B is released and both particles start to move. How are they going to start moving? Just look at the masses. A is 0.2 kilograms and B is 0.6 kilograms. So this is heavier than this. This is going to start moving like this, all right? When B reaches the floor, it remains at rest, but A continues to move vertically upwards until it reaches a height of 3 meters above the floor, right? Think of it a little bit. This one starts going down. This one starts going up. At every single moment, the speed of both are the same. The acceleration is the same throughout. And the distance they cover is the same, all right? In terms of displacement, the displacement of B is going to be down. The displacement of A is going to be up, but the magnitude is the same. If this one goes 1 meter down, this one goes 1 meter up, right? The moment B hits the ground and stays there, the reason that caused the moment, the motion, which is the tension in the string, ceases to exist, right? So when you let this go, I have a diagram here already, did it with the forces already, okay? So you have here the weight of B, which is bigger than the weight of A, right? When you let A go, the weight of B is going to be bigger than the tension that immediately is going to be to appear in the string. These two tensions need to be the same. Again, you have a single string passing over a smooth pulley, all right? That this tension needs to be smaller than this weight, but at the same time needs to be bigger than this weight over here. Otherwise, this one wouldn't go down and this one wouldn't accelerate up, all right? So every time you make a sketch like this, it then doesn't take too long. Just make the size of the arrows in a way that just by looking at this, you know what's going to happen, right? So this one goes down, this one goes up. Accelerating down, accelerating up. This one touches the ground and stays there. This one doesn't stop immediately, right? Because you have inertia, right? It is going up, and the moment it will take the marker as the object. The moment it leaves my hand, it still goes up a little bit, right? And the question is going to be the total height. No, it's going to be the value of h, right? For you to calculate the value of h, you have to think of the total height that you are given. The total height is 3 meters, all right? So you know that the height at the A is, when it stops, is 3 meters, right? That's what I have over here. This is the moment when it stops. And what are these 3 meters? These 3 meters are the distance B covered, right? Which is 1.6 meters. Don't forget, B goes down 1.6 meters and A goes up 1.6 meters. It's going to be the value of h, right? So you have h plus 1.6 plus that little tiny distance that it still goes up just before it stops. That's what 3 is. These 3 meters is the h, the 1.6. Is the h, the 1.6 meters that this one goes down, and that tiny distance that it still goes up because of inertia. All right? So that's how you're going to calculate h. You already know this. Once you know this, you can get the h. So you have to know that distance. All right? So how do you get that distance? Again, forces. You have this correctly represented. Just a matter of putting this in math language, and that's what I did over here. For A, you have T minus dfg of A equals ma A, all right? Tension minus the weight of A equals the mass of A times the acceleration. For B, you have the weight of B minus the tension equals the mass of B times the acceleration. Look, I always put this in a way that it all becomes positive, right? So look that I put the tension minus the weight so that this acceleration is positive. I know that it's going that way, so I put this minus this, all right? I put the bigger minus the smaller. But on B, I did the same thing. I put the bigger minus the smaller. This means that the acceleration calculated is always going to be the same. It's a trick just to speed things up, all right? And then again, I put for both, all right? If I put for both, if I take this as a single object, as a system, I eliminate the internal forces, which are the tensions, and I just have FG of B minus the FG of A equals the total mass times the acceleration, which is always the same. All right? And this is the one I'm going to use because I need the acceleration to plug it in the formulas for kinematics to get that height. All right? Don't forget that I already know that the maximum height is going to happen when the speed is 0. That's where it stops, right? So I have V as being 0. I need to get the speed with which A is when this one hits the ground, all right? And that's what I'm getting right now by calculating the acceleration, all right? I know now the acceleration. I just plug in the values, I get the acceleration. Then I can use this formula over here to get the speed with which B hits the ground, which is the same as the speed with which A is, and it's going to be the initial speed to calculate this value D, all right? So V of B equals U of B, which is 0, plus 2AS. I already know A, right? I already know S is 1.6. So I substitute, I just make the formula in terms of B, then I just plug in the values, and I know the value of V of B is 4 meters per second. So B hits the ground with 4 meters per second, and A is also at 4 meters per second when the tension disappears. When the tension disappears, what is going to be the only force acting on B is the weight, which is pointing in the opposite direction of motion. So A is going that way. When B hits the ground, the tension disappears, and you only have the weight, which is going to slow it down to the maximum height. See? And now I know the value of that speed, which is now going to be the initial speed on the new formula over here. All right? Actually, the formula is the same, but for the last part of the motion. Now, this is the speed at the maximum height, which is 0. This is the initial speed for that tiny section of motion, which we just calculated, is 4. The acceleration is just G, all right? You don't have any more force, just the weight. So the acceleration is going to be the acceleration of gravity. And this is how you calculate D. Plug in the value, solve it for D, and you know that D is 0.8 meters. So again, these 3 meters are composed of the 1.6 meters A went up while B was going down, the 0.8 meters that A still had to go up until it stopped, plus H. So put it over here, and you get the value of H as being 0.6 meters. All right? Okay, let's look at the last one that I have here. This is from November 2009, paper 41, question 6. Let me just see the total marks that you have on the previous one. It's 6. It's a 6-mark question. This one is a total of 5. It's 10 points for this one. But it's broken down, right? So it would be easier in the sense that you could get marks in individual questions, and you might lose at the end, but you would always be able to collect some points along the way. This could be as well, such as this question, could be a 10-mark question, all right? Instead of being broken down into smaller parts, you could have all the questions in a single one, right? Just like the one that we saw. But it's not. So let's look at it the way it is. Particles P and Q of masses 0.55 kilograms and 0.45 kilograms respectively. So 0.55, 0.45. So this is going this way once it is released. Are attached to the ends of a light and extensible string which passes over a smooth fixed pulley. The particles are held at rest with a string taut, so you have tensions, and its straight parts vertical. Both particles are at a height of 5 meters above the ground, and the system is released. When it is released, the heavier goes down, the lighter goes up, right? Find the acceleration with which P starts to move. All right, you probably already know the mechanics of it, literally. And the best way to calculate the acceleration of a system is to consider it as a whole, all right? Anyway, you have here the representation of the forces again, the weight of the P, the weight of Q, and the tensions. done in a way that this is bigger than that, this is the same as this, and this is bigger than that. All right. So this one accelerates down, this one accelerates up with the same acceleration. Right. I already put here the weights. Okay, just multiply by 10. And the initial velocities of P and Q at 0 meters per second. I wrote everything there. Positive is going to be that way. Okay, so up for Q, down for P. If I consider it as a whole, I don't have to worry about the tensions. So I just have this weight minus that weight. All right. Don't forget again, they are both pointing down, but I'm considering positive this way. So this one is a positive force. This one is a negative. Okay. If you use this trick, everything is going to be much smoother. Then you have it that way. So the resultant force, which is this minus that, equals the total mass of the system times the acceleration. All right. This is 0.55. This is 0.45. These two masses put together, they are just 1. All right. So the acceleration is 1 meters per second squared. You already know the acceleration. Okay. So you already know 3 points with this out of 10. The string breaks after 2 seconds, and in the subsequent motion, P and Q move vertically under gravity. So what's going on over here? This starts going down, this starts going up. But you won't have the tension in the string all the way until P hits the ground. Somewhere in between, the string is going to break, and they are just going to fall under gravity. What does this mean? This means that from a certain point onwards, P is just going to fall with an acceleration of 10 meters per second. And Q, when this happens, is also going to submit it to the same acceleration of 10 meters per second squared, 10 meters per second squared, pointing down. So what's going to happen to Q? Q was going up, right? So you have now an acceleration downwards. So Q is going to slow down, stop, and eventually fall, right? With the remaining of the string, whose weight you don't have to worry about. Okay? So again, while the string is there, not broken, this one accelerates down, this one accelerates up with an acceleration of 1 meter per second square. The string breaks. This one is going to go the remainder of the height with an acceleration of 10 meters per second square. This one, with the same acceleration of 10 meters per second square, is still going to go up a little bit until it stops and then falls, right? So this is what's happening. Now you have to adapt the situation that you already understood using the laws of mechanics that you've learned, okay? What is the question? At the instant that the string breaks, find the height above the ground of P and Q. So you want to know the height above the ground of P and Q the moment the string breaks. So for you to think of the mechanics of this, you have to consider the string complete, not broken. So you have still considered the tensions, which means that you have to consider the acceleration that you just calculated there, right? So you just have to use the kinematics formulas that you've learned. And the best one, since you know that you want the time, no, you want the distance, and you are given the time, right? Yeah, 2 seconds. The best one is the S equals ut plus 1/2 of at squared, right? Let's do it for P, okay? So you want to know this distance over here. U is 0, right? It starts from rest. T is 2 seconds, and A you just calculated over here is 1. Substitute it, and you have a distance of 2 meters. So P went down 2 meters, but this is the same distance that Q went up. The question is, calculate the height above the ground for both, all right? So the height above the ground for P is, it started as 5 meters, it went 2 meters down, so it's going to be 3 meters, right? But Q is going up, so it started at 5 meters, it moved up 2 meters, so it's going to be at 7 meters, all right? So another 2 points. The speed of the particles. In order for you to get the speed of the particles, now you use V equals U plus AT. Again, U is 0. The speed is going to be the same the moment the string breaks, right? So you only have to make the calculation once. The acceleration is 1 meter, 1 meter per second squared. The time is 2 seconds, as the question said. So just substitute, and you have a speed of 2 meters per second. So when the string broke, the particles were moving at 2 meters per second. This one with a velocity of 2 meters per second. Actually, both velocities were positive because the motion is like this. Finally, I think the last question. Yeah, show that Q reaches the ground 0.8 seconds later than P. So this one hits the ground. Okay, but yeah, the string breaks. This one hits the ground. But when this one hits the ground, what is happening to Q? Q is still going. You have to figure out what happened to Q because it might be still going up before it actually changes direction and moves down to hit the ground. Okay, so the time for P to reach the ground after the string breaks is, and now you can calculate it because you know the height at which, you already know the height at which P is. It's 3 meters, right? So plug it in the formula S equals ut plus 1/2 of gt squared. Pay attention that the acceleration now is 10 meters per second squared. You no longer have tension, so the only acceleration is the acceleration of gravity. Okay, everything is positive because P is going in the direction of motion, which in these situations I decide to be positive. So this is 3, this is 2, the u, okay, we just calculated. The t is what we want. G is 10. Now solve the quadratic. Solve the quadratic, and you have two times. One is -1, which cannot be, is a negative time, and the other one is 3/5 or 0.6 seconds. So P takes 0.6 seconds to reach the ground. All right? What about Q? You can use the exact same formula. You just have to worry about the signs. All right? The time for Q to reach the ground after the string breaks is, and now you use the same formula, but pay attention to this. Don't forget what positive is. Positive is that way. So the moment the string breaks, what is the displacement value of S? Is going to be not 7, but -7, right? In relation to the position of Q when the string breaks, the height is a negative, if you take it as a displacement, is a negative vector. It points down, right? So that's what you put over here, -7. The u is positive. The velocity when the string breaks is pointing in the direction of motion, so it's a positive value. The acceleration is negative. It's pointing in the opposite direction. Here it wasn't. Here the acceleration, the 10 meters per second square, was in the direction of motion, which I considered positive. Okay, so I left it with a plus. Here I already put myself a minus. And then I just solve the quadratic the same way. And I find the value of t. Again, you have a negative time, that doesn't matter. And the other one is 7/5, which is 1.4 seconds. So this one takes 1.4 seconds to reach the ground after the string breaks. You want to prove that the time difference between them is 0.8 seconds. So you just do 1.4 minus 0.6, which is 0.8 seconds. I hope that with this question you understand the importance of the signs in these equations, the fact that they are vectors, and the importance of deciding the positive and the negative value, not in terms of directions up, down, or left, right, when you have pulleys, but in terms of the direction of motion. All right? Everything that points this way, velocities, accelerations, and displacements, is positive. Everything that points in the opposite direction, again, accelerations, displacements, and velocities, they are negative. If you do this correctly and plug in the equations that you already used to work with, then the results are going to show up naturally. Okay?